In July 1976, NASA's Viking 1 touched down on the surface of Mars. Getting there at all was an incredible feat of engineering, especially considering the planet was already notorious for being a graveyard for early space missions. The data Viking sent back painted a bleak picture. It revealed a freezing, bone-dry world with a whisper-thin atmosphere. The onboard biology experiments found no clear signs of organic material, and the surrounding landscape appeared totally inert. For decades, those early images anchored our understanding of the planet. Mars was cemented in our minds as a completely static, lifeless rock, frozen in time. Today, a new generation of rovers is reading the Martian surface with far more precision. Curiosity, for instance, has spent years mapping complex layers of carbon and ancient weather history across the terrain. While exploring a region known as Jawbone Canyon, researchers reviewing Curiosity's panoramic images noticed something strange. Tucked right beside the rover were slabs of sedimentary rock stacked with delicate millimeter-scale ripples. On Earth, we know exactly what causes patterns like this: heavy grains of sand violently pushed into ridges by the wind. But the modern Martian atmosphere has less than 1% of Earth's surface pressure. It can lift fine dust, but it lacks the physical muscle to push heavy sand grains into these formations, which presents a problem. If the air is too thin to move the sand, how was this violent weather pattern carved into solid stone? Geologists call these structures supercritical climbing ripples. They form when rapid, forceful bursts of wind dump sediment faster than the dunes can actually migrate. Picture a fast-moving current of air rushing over the crest of a dune. As it passes the peak, the wind decelerates rapidly and drops heavy sand vertically in place. Each new ridge climbs directly onto the back of the one before it. Because these ridges stock and lean in one specific direction, they permanently lock the ancient wind's compass heading into the geological record. In Jawbone Canyon, the layers show the wind was blowing hard from the south. Lifting and packing those heavy grains requires immense atmospheric pressure. The very existence of these ripples proves that 3.5 billion years ago, Mars had a dramatically denser, heavier atmosphere. The rock layers even record the exact pacing of the event. Between the steep ridges are flatter bands, showing where the winds paused. We are looking at furious 6 to 20-minute wind gusts packed inside a storm system that lasted for hours. These stone layers function as a geological stopwatch, preserving an afternoon of violent weather from billions of years ago. And this wasn't an isolated local squall. Zooming out to the vast canyon system of Valles Marineris reveals evidence of a massive, active climate system. This terrain map on the bottom left shows what scientists call paleobed forms, ancient sand dunes. Their shape and parallel rows indicate they were constructed and sculpted by strong, planet-wide equatorial trade winds. To understand how they survived, look at the spectral graphs on the right. They show a basaltic and sulfate-rich composition, indicating the dunes went through lithification, likely cemented by groundwater upwelling or sudden burial under volcanic ash. They hardened so quickly that these massive structures were frozen in time as complete landforms, long before the wind could erode them away. The micro-ripples in Gale Crater and the massive petrified dunes in Valles Marineris reveal an early Mars that was violently active, windswept, and wet, which leaves us with a massive planetary mystery. If Mars was once wrapped in a thick atmosphere and carved by heavy storms, where did that air go? The answer is being tracked by the Trace Gas Orbiter. Observing vertical gas movements during extreme weather revealed a mechanism inside modern Martian dust storms. These massive storms act as a thermal elevator. They grab trace amounts of water vapor and push them high into the upper atmosphere. Without a protective magnetic field, that high-altitude water vapor is exposed. Solar winds sweep in, stripping the molecules into space. This dust-driven escape mechanism has been running in the background for eons, slowly bleeding a dense, life-supporting atmosphere into the vacuum of space. The barren world Viking photographed 50 years ago is just the end of the story, a desiccated remnant where rushing water gave way to sand. Modern explorers are now looking beyond the dusty surface to read the deep geological record. Decoding a 3 billion-year-old sandstorm preserved in stone, proves that Mars had the air pressure, the weather, and the dynamic climate to potentially support life. By reading these petrified weather reports, robotic explorers are finally bringing the ghosts of a living Mars back to life.